I'm Anil Kumar. Welcome to my series on complex numbers. In this introductory chapter, we'll discuss many points. Some of them are listed here. We'll talk about the number system in general and see why these complex numbers were introduced and figure out when are the two complex numbers equal, how to solve equations related to complex numbers. We'll do few operations with complex numbers and also find relations with conjugate of complex numbers. We are going to do all that with some practice examples. So to begin with, let me share with you list of practice examples which we'll solve while understanding all about complex numbers. So here we have 13 questions. You can pause the video, copy these questions, answer them also, and then we'll pick them up one by one and understand how the different topics which we are talking about relates with these questions. So I'll keep this list separately and take one of these examples while explaining the concepts. So let's begin with the number system which we know. We talk about natural numbers, n. So these are natural numbers, so correct. When we say natural numbers, what do we mean? Natural numbers are like 1, 2, 3, 4, right? So they do not include 0. Then we have whole numbers, right? So we call them as whole numbers. And whole numbers means 0 is introduced. So every time while working with the number system, whenever there was a need, we introduced something and we called it a different number system, right? So then we had integers, which is represented by I or by Z, right? So as integers. With integers, we introduced positive and negative numbers, right? So we had numbers like, let me write positive and negative, 1, 2, 3, 4, right? And so on, and we also included 0, right? Okay. Now this was not just the only one. We had these rational numbers. So let me write rational numbers. Symbol is this letter Q. So rational numbers were of the form of P over Q, right? Where Q is not equal to 0 and P and Q belongs to the set of integers. And then we came up with numbers which were not rational. So we'll call them as irrational numbers. But since these are also real numbers to work with, these irrational numbers, you cannot write them in P by Q form. To give an example, square root 2, right, pi. So these numbers, which are non-terminating decimal numbers, are called the irrational numbers. So to include them, we introduced real numbers. So real numbers is basically combination of rational and irrational numbers. So that is what we all know about a number system. Now, we came up with questions while working with quadratic formula. To give you a reference, in quadratic formula we have if we have where we have x is equals to minus b plus minus square root of b square minus 4ac divided by 2 times a, right? This is when we are trying to solve an equation which is ax square plus bx plus c equals to 0. Now in quadratic formula, we figure out that if b squared minus 4ac is negative, that is to say it is less than 0, then we say we have no real solution. Now this no real solution means what? Means we are restricted on our number system, right? So that means we have to expand number system. Correct? And the main reason for no solution was basically that square root of a negative number was not defined. So we expanded this to the set of complex numbers. Correct? So that is how we got to the complex numbers. And now, on the new fresh page, we will now look into what these complex numbers are. So now, let's talk about the complex numbers. In general, we have understood that iota I is equal to square root of negative 1, right? Or you can say that I square is equal to negative 1. So we now have square of a number can be represented for a negative number. That's the whole concept. So generally, we express complex numbers with letters like z, and we'll write them as z as equal to a plus bi. Now whenever you write in this form, in that case you should remember that both a and b belongs to set of real numbers, right? And we name this as the real part of the complex number, and this is the imaginary part. Let me also introduce you to the conjugate of this. So we do write sometimes a number with z star, which could be written as a minus bi. Now this is conjugate of the complex number z. It is also written at times with a bar on the top. So either way, we could write conjugate of a complex number. Now this conjugate of a complex number leads to many important properties. You will notice that if you add the complex number with its conjugate, then what do you get? So if I add these two, the real parts adds up and the complex part or the imaginary part cancels out. So that is equal to 2 times the real part a, right? So you can also write that the real part of a complex number is basically equal to half of the sum of the conjugate and the number itself. Is that clear to you? So sum is always a real part. Now if I do the difference between the complex number and its conjugate, then what do you get? So a and a will cancel away, but here they will double up. So we get 2 times bi, right? So in that case, bi, which is the imaginary part of the complex number, is basically equal to half of the difference of the complex number and its conjugate, right? Now what do you get when you multiply the complex number with its conjugate? So if you do that, which is to say that we are doing a plus bi times a minus bi, right? So that should be equal to a square minus bi square or plus b square. So what do you get here? The product of complex number and its conjugate is always equals to squares, sum of squares of their real parts, the coefficients, right? So these are few important properties which we should keep in mind while working with complex numbers. Now to explore further, here are few examples. If a complex number z is equals to 2 minus 3i and w is equals to 1 plus 2i, you need to find the value of z plus 2w, z times the conjugate of the complex number, and the product of these two complex numbers. You can always pause the video, answer this question. Now let's look into part A, which is what is z plus 2w equals to. Now z is 2 minus 3i, so we could write this as equal to 2 minus 3i, which is z, plus 2 times w, which is 1 plus 2i. So you let me write them, expand it first. 2 minus 3i plus 2 plus 4i. Combining the like terms, we get 2 plus 2 as 4, and minus 3i plus 4i gives us I. So what we get here is 4 plus I. So you combine the real parts with the real parts and the complex parts with the complex parts to do this operation of addition. Now let's see what happens when we multiply the complex number with its conjugate. So let's do part B now. So we'll do the product of the complex number and its conjugate. So here it is 2 minus 3i times the conjugate will be 2 plus 3i, correct? So when you multiply this, you get 2 times 2. So we have to do the distributive property. Multiply with 2 first, both the parts. So we get 2 times 2 as 4. 2 times 3, 6, right? So plus 6i. Now with minus 3i, we get minus 6i, and that gives you minus 9i square. Now, minus 9i square is basically plus 9, right? So what we get here is 4 plus 6i minus 6i is 0 plus 9, which is equal to 13. So as you can see, in short, z times its conjugate is basically equals to 2 square plus 3 square, right? Which is 4 plus 9 equals to 13. Is that clear to you? So the property which we just looked into, right? Now let's do C. Which is, what is z times w equals to? The complex number 2 minus 3i times the complex number 1 plus 2i. So we'll apply the distributive property. 2 times 1 is 2. 2 times 2i is plus 4i minus 3i. And that gives you minus 6i square. And this is equal to 2 plus 4i minus 3i, and I square is negative 1, so it becomes plus 6. So you can combine the real parts and the imaginary parts. You get 6 plus 2 as 8, 4i minus 3i is I. So that becomes your answer. So z plus w is equal to 8 minus I. Is that clear to you? So that is how we can perform operations with the complex numbers. So I hope this part is absolutely clear. We'll take up now a few equations to solve with complex numbers. Just to solve the equation, which is x squared minus 2x minus 3 equals to 0. Now this equation can be solved in many different ways, but we'll use the quadratic formula, right? So we say x is equals to minus b, which is 2, plus minus square root of b squared. so which is minus 2 square minus 4ac, so 4 times minus 3 square root divided by 2. So when you do that, you get 2 plus minus square root of, so that is 4, and this is plus 4 times 3 is 12 divided by 2, or what we get here is 2 plus minus, that is 16, square root of 16 is 4 over 2, right? So that does give you two solutions. One is 6 divided by 2, which is 3, and one is minus 2 divided by 2, which is minus 1, right? So we have two solutions for this, and we can say, well, x is equal to 3 or x is equal to minus 1. Now let's take the second example here. The second example is 9x squared plus 1 equals to 0. Well, this is much simpler than the previous equation. You could now write this as 9x squared equals to minus 1, or you can say x squared is equal to minus 1 over 9. Now as soon as you get this, we say we have no real solutions for this, correct? So as soon as you get this, we have no real solution. Why? Since square is always a positive number, right? Not negative, correct? Now we can only get a solution if we could extend this, and then we extend it to complex numbers. Well, basically it really meant that we have to take care of square root of negative number. So we said square root of negative 1 is equal to this number iota. So this I is also referred to as iota, a Greek alphabet, and a name, iota, I. So that was the introduction of the complex numbers. To take care of square root of a negative number. Does it make sense to you? Perfect. So now, if I have to solve this equation, I will say x is equals to plus minus square root of negative 1 over 9. Which you can think like this, which is equals to plus minus square root of negative 1 times square root of 1 over 9. Now square root of negative 1 is iota for us in the set of complex numbers, and square root of 1 over 9 is 1 over 3. So we can write this as plus minus 1 over 3i. Correct? Now that becomes a complex number, this iota, which is square root of minus 1. Correct? Now in general, we will be writing complex numbers in the form of a plus bi, right? So generally, we'll write complex numbers as, we'll use the letters like z equals to a plus bi, and that is how we are going to write complex numbers. Now here, a and b both are real, right? So a and b are real numbers. Iota is square root of minus 1, right? So where a and b belongs to set of real numbers. Is that correct? And z is our complex numbers. Z belongs to set of c, the complex numbers. Is that clear to you? So that is a short introduction to our complex numbers, and now you understand that iota is square root of negative 1, and that helps us to solve such equations also. Perfect. So let's move forward and explore more about these complex numbers. So we'll take a few examples and also illustrate the properties. Now we'll talk about equality of complex numbers, right? So in this example, we have two complex numbers, z and w. So normally we'll be writing complex numbers with these letters is Z, W, U, V and such letters, right? We'll leave X, Y and A and B for real numbers in all our examples. Now many times you will also see the complex numbers written with bold letters. Now the question here is Z equals to 2 minus A plus 2B plus 1I and W is 3B plus 1 minus A plus 1I. We need to find the value of A and B for Z equals to W. So if two complex numbers are equal, then how do we solve such an equation? Well, it is kind of important to understand when we say equality of complex numbers, we really mean that real parts are equal and complex parts are equal. So both should be satisfied for equality. So in general, if I have a complex number Z as A plus BI, and if I have W as C plus DI, and if Z is equal to W, it really implies that A is equal to C and B is equal to D, right? So these are the two complex parts. You can write I also, but you can write the coefficients also, right? So that really means that A is equals to C. That means the real parts are equal and the complex parts B and DI are also equal. So we have written B and D, I and I cancel. Is that clear to you? So that is the concept. With that, we are going to solve this particular question. And now, what we have here is that Z is equal to 2 minus A plus 2B plus 1I, and we are given W as equals to 3B plus 1 minus A plus 1I. Now if Z equals to W, then we have two equations, and that is 2 minus A should be equal to the real part 3B plus 1 and 2B plus 1 should be equal to minus of A plus 1. Is that clear? So this is when complex numbers are equal, that really means that the real parts and complex parts, you can say coefficients, are also equal. Correct? Now that should help us to solve for A and B, right? So we'll just rearrange these equations, get our new equations, and then method of substitution or elimination can be adopted to get the value of A and B, right? So from the first equation, taking A to the right side, we get 3B plus A equals to 2 minus 1, which is 1, correct? And from the second equation, we get 2B plus A equals 2. Taking 1 to this side, minus 1 is minus 2. Correct? So as you can see, we get these two equations, right? This is from 1 and this is from 2. Correct. Now, to solve them, if I do equation 1, let's call this as our equation 3 and 4. So if I do equation 3 minus equation 4, what do I get? So if I do 3 minus 4, I get B, A and A is 0, right? We get this minus this is 3. So we get B equals to 3. So let's call this as our equation number 5. And now we can substitute B and find the value of A, correct? So we can substitute B in equation 3. So we'll sub 5 in, let's say, 4. So if I do that, we get 2 times 3 plus A equals to minus 2. and that gives me a equals to minus 2 minus 6, which is minus 8. Correct. So we get our solution. So our solution in this case is that a is equal to minus 8 and b is equal to 3. Is that clear to you, right? So that is b and this is a. So with the help of this concept that the complex numbers are always equal only if their corresponding real parts and complex parts are equal, correct? So that is extremely important to understand, and that helps you to solve many equations related with complex numbers. So I hope this concept is absolutely clear. So let's move forward and solve and check some equations. So here we'll take a few questions from this practice sheet. At this stage, I'd like you to actually pause the video and try to solve first few questions of this worksheet and then watch my video. I hope that really helps. So here is a practice question for you, question number 3. You need to solve this equation x squared minus 4x plus 13. Now we can solve this using quadratic formula. So we can write this as x is equal to minus of b, which is 4, plus minus square of this, which is 16, minus 4ac, which is 4 times 13. Right? C is 1. If you want, you can write. And 2 times a, which is 2 times 1. So that gives you 4 plus minus square root of 16, and 4 times 13 is 52. Divided by 2. So that gives you a negative number within the square root. Do you see that part? So we have negative number within the square root, and we get negative 36 within the square root. So we know that square root of a negative number is iota I, square root of 36 is 6, so we can write this as 4 plus minus 6i over 2. And that gives you two equations, two answers, which is, you can write here, two answers as dividing by 2, we get 2 plus 3i, and the other one is 2 minus 3i. Now, whenever you get a solution of a complex roots, you'll find they are in conjugate pairs, right? So this is referred to as a conjugate pair. Correct. So 2 plus 3i and 2 minus 3i are conjugates of one another. Now, that is the part of solution. Now we need to check if our solution is correct or not. So let's try to check this. So we will check for x is equals to 2 plus 3i and also x equals to 2 minus 3i. So if I substitute in the equation 2 plus 3i, what do I get? So our equation is x squared minus 4x plus 13 equals to 0. So if I substitute 2 plus 3i, I get 2 plus 3i whole square minus 4 times 2 plus 3i plus 13. Right? So let's say equals to 0. So when you expand, you get a square, which is 4, plus 2ab, which is 4 times 3 is 12i, plus b square, so which is plus 3i square. I'm purposely taking extra step here to show you that I square is negative 1, so that will change. Now we'll multiply this with 4, distributive property, we get minus 8 and minus 12i plus 13 equals to 0. Now here we get 4 plus 12i, I square is negative 1, and so we get negative 9 here, and we have negative 8, negative 12i plus 13 equals to 0. Now let's bring the numbers together. We get 4 minus 9 minus 8 plus 13, and the complex parts are 12i minus 12i. We need to show that this is equal to 0. Now 4 minus 9 minus 8 plus 13 is 0, and this is also 0, so we get 0 equals to 0, correct? So that is the correct check. Is that clear to you? Perfect. Now as an exercise, what you should do is, you should check for the second part, which is, if I write 2 minus 3i whole square minus 4 times 2 minus 3i plus 13, you'll find that this is also equal to 0, and that will be your check, right? So you should try. Is that clear to you? Perfect. You'll find that both are true. So now let's move on and take another example. This time the example has, we have used z. So to make it very clear that we're talking about complex numbers, we have avoided a, b and c now. We are using z instead of x and y, right? But the equation is slightly different. It's z squared minus 6iz minus 9 equals to 0. Now let's figure out what kind of answer do we get for such an equation. So now our equation to solve is z squared minus 6iz minus 9 equals to 0. So z, using the quadratic formula, will be 6 plus minus b squared, 6i, not 6, right? Since we now have the value of a as 1, b is minus 6i, right? So in this particular case, what we have is a equals to 1, b equals to minus 6i, and c equals to minus 9, correct? Okay. So b squared minus 6i whole square minus 4 times a is 1 and c is minus 9 divided by 2 times 1. Clear? So we get 6i plus minus square root. Now square of minus is positive, 6 is 36, and I square is negative 1. So we actually get here minus 36. Correct? On this side, minus and minus is positive, so you get plus 36. And then what we get here is 2. So this could be written as, and that is 0, right? So we get 6i over 2. And the answer for us now is 6i divided by 2 is 3i. Do you see that? So at the moment we have got one single answer, which is just 3i, correct? So we did not get a conjugate pair. So note, not a conjugate pair. Do you see that? So sometimes if our equation is as shown here, we may get a solution which will have just one number, which is a complex number in this case, as a solution of our quadratic equation. And this happens to be a complex part, right? A pure complex part. Now let's check this solution. So I'll write 3i for z. So we are going to check by substituting the value in z squared minus 6iz minus 9 equals to 0. So when I substitute 3i here, we get what? We get 3i whole square minus 6 times 3i. Right, so I and 3i again. So for z we have put 3i. And we have put I as separately, this I here, minus 9 equals to 0. So that gives you minus 9, right? So basically this is 9i squared. Let me write like this. And that is 6 times 3 is 18. and I square minus 9 equals to 0. Now 9I square is negative 1, so we get minus 9, and here I square is negative 1, we get plus 18, and we have minus 9 equals to 0, and we do get 0 equals to 0, which is 2. Do you see that part? So here we have only one solution. So an equation involving complex numbers can have just one solution also. And this time the solution is a pure imaginary number. (3i). Do you see that? So sometimes you do not have the real part in the solution, and there could be just one solution. Clear? Let's take another example to illustrate another point. This time we are going to solve the equation which is z square minus 2iz minus 2 equals to 0. In this case, a is 1, b is equals to minus 2i, and c is equals to minus 2. And therefore, we can write down the solution of z as equals to 2i, right, minus of this, plus minus, square root of minus 2i square, minus 4 times a is 1 and c is minus 2. Divide by 2 times 1. So which gives you 2i plus minus square root of, so that is minus square is positive, 2 square is 4, but I square is minus 1, so we get minus 4 here. And here we get minus and minus is positive, so we get positive 8. Divided by 2. Now that gives you 2i plus minus. Now that is square root of 4, which is plus minus 2 over 2, correct? So what do you notice here? Well, in this case, we have two solutions. Clear? In this case, we have two solutions. One of the solution is I plus 1. The other one here is I minus 1. Does make sense? So we have two solutions, I plus 1 and I minus 1. Now, are these conjugate pairs? So the question for you here is, question, are I plus 1 and I minus 1 conjugate pairs? Right. So answer this question. Now let us try to check this out. So now let's do the checking part. Okay. So to check, I will write down I plus 1 here. So we get I plus 1 whole square minus 2i times I plus 1 minus 2, right? Now that gives you I square plus 2i plus 1, and this gives you minus 2i square minus 2i minus 2, right? So I square is negative 1 plus 2i, and here we have positive 1, and I square is negative, so that becomes positive 2. Here we have minus 2i and minus 2. So clearly you can see here that 2i and minus 2i cancel. We have plus 2 and minus 2 cancel. And we also see that this is also cancelling. So we do get our solution, which is that this is equal to 0. Perfect. So it works. Let us also check with I minus 1. So if I have I minus 1 whole square minus 2i times I minus 1 minus 2. What do we get? So I square, we get I square minus 2i plus 1. And here when you expand, you get minus 2i square plus 2i minus 2. I square is negative 1 minus 2i plus 1. Here this becomes plus 2 since I square is negative 1 plus 2i negative 2. So here also you can cancel negative 1 with positive 1. You can cancel minus 2i with plus 2i and also 2 with 2, and this is also equal to 0, right? So both are correct answers. Is that clear to you? Now, important thing here is that they are not the conjugates, right? So are they conjugate pairs? 1 plus I, the conjugate is 1 minus I. Correct? So are these conjugate pairs? No. So what you learned here is that if you have an equation which involves I in this fashion, you might have one solution, you might have two solutions, and both these solutions may not be just conjugate pairs, right? So you only get conjugate pairs in cases which are like our quadratic equations without I in between. Is that clear to you? It's very important to note this. With that in mind, let's move forward and now look into operations with complex numbers. Now let us explore some properties of the complex numbers and their conjugate. The question here is to show that sum of two complex numbers and their conjugate is actually sum of the conjugates itself. And here we are saying that show that the conjugate of the product of two complex numbers is product of two conjugates. To prove what we will do, we'll just take two complex numbers, z as a plus bi and w as c plus di, right? We'll use these two complex numbers to explore. So the conjugate, which can also be written with a bar on the top, with z will be a minus bi, and for w it will be c minus di. So these are the conjugate. So now let's explore the properties. So the first one is z plus w conjugate. So z plus w, let's say z is a plus bi. So we have a plus bi plus w is c plus di. So we have c plus di conjugate, right? Now we can combine the real parts, which is a plus c, and we can combine the imaginary parts, which is b plus di. Right. And we have to find the conjugate of these. So the conjugate of this is indeed equals to, the real part is a plus c, which remains same, right? So that's the real part. As far as the complex part is, it becomes minus of b plus d of I, correct? So the conjugate of this sum of two complex numbers can be written as this. Now we need to show that this is equal to the sum of their conjugates, right? So let's do part B of this, which is, let's open this bracket. So I could write this as a minus b, so a minus bi, just rearrange, right? So basically what I'm doing here is I'm combining a with bi, and I got plus c minus di. Good. Now that can be written as, that is conjugate of z, right? And this is conjugate of W. Is that clear to you? Right. So we have shown that the sum, we could also write with a bar on the top, is basically equal to the sum of the conjugates. Is that clear to you? Now this is a very important property which has been proved here. Now let's take up the next part where we'll see what happens when we multiply them. So the product of two complex numbers and then their conjugate, we can write like this: a plus bi with c plus di, and then we'll do their conjugate, right? So when you multiply, you get a times c, a plus di, b ci, and when you multiply these, I squared is negative, so you get minus bd. And that is, combining the terms, we get ac minus bd. So that's the real part. And the complex part here is plus AD plus BC. Conjugate of all this is, we'll get a negative sign here, right? Will be AC minus BD minus AD plus BC. Is that clear to you? Correct? So that's what you get. We need to show that this is the same as the product of their conjugates. Now let's find what is the product of their conjugates. So product of conjugates, let's write with this nomenclature, will be a minus bi times c minus di, correct? Which is AC minus ADI minus BCI, and when you multiply this, you get plus BD. And that is equal to AC minus BD, combining the like terms, minus AD plus BCI. Is that clear to you? So you can very clearly see that both are equal. So from here, we know that both are equal, right? So both are equal. So that is how we can show that the product of conjugates is same as, you can first multiply and then take a conjugate. I hope that makes sense. Now with this we have learned basics about the complex numbers. I will now like you to explore these complex numbers further. So I'd like you to pause the video, answer these 6 questions, and then we'll take them in part 2 of our series. I hope that makes sense. Discuss solution of question number 8 to 13. I'd like you to pause the video, copy these questions, answer them, and then look into my suggestions. So let's begin with question number 8, which is very much related with question number 9. Question number 8 here is, expand z minus alpha times z minus beta, and 9 is find the equation whose roots are 3 plus 4i and 3 minus 4i. So let's answer question number 8 first. Expand z minus alpha times z minus beta. So when you expand, you get z square minus beta z minus alpha z and the product of these two, so plus alpha and beta. So that gives you z squared minus, taking z common, you get alpha plus beta. I've rearranged them, right? Plus alpha times beta. So here, what you learn is that if alpha and beta are roots, then the equation could be written as z squared minus sum of roots times z plus product of roots. Is that clear? So that is how you would actually write the quadratic form of the equation knowing the roots. Now, question number 9 is, we are given the roots, right? So the two roots, let's call them as alpha and beta. So alpha is 3 plus 4i and beta is 3 minus 4i. Now these roots are conjugate roots. We need to find the quadratic equation with these roots. So we can write that the quadratic equation will be written as, since these are the roots, we can write this as z square minus sum. So what is sum of roots? Alpha plus beta is 3 plus 3, right? So which is 6. Sum of roots with a negative sign, right? Plus the product of roots. Now how do you find the product of roots? The product of roots is basically a square plus b square. That is the product of roots, right? So the product root is 3 square plus 4 square equals to 0. That will be your equation. Correct? So you get your equation as z square minus 6z plus 9 plus 16 is 25 equals to 0. Correct? So that is how you could actually get your equation. Now what it did here was, we did alpha plus beta as equal to 3 plus 4i plus 3 minus 4i, right, which is 6, right? That is the sum of roots. And we wrote alpha times beta as 3 plus 4i times 3 minus 4i, which is equals to 3 times 3, a square minus b square, right, minus 4i whole square, right, which is 9 plus 16 equals to 25. Is that clear to you? So that will help you to understand how we kind of related first and the second question and wrote our equation. So if we qualify with the word roots, that means all this is equal to 0, right? And therefore we get that equation. Is that clear? Now let's look into question number 10. Question number 10 is to expand and simplify 2 plus 3i cube. So let's do it. We get 2 plus 3i whole cube. So we could write this as 2 plus 3i square times 2 plus 3i, right? So square is a square, which is 4, 2ab plus 4 times 3 is 12, 12i, plus b square, which is 9i square, right, which is 9i square, times 2 plus 3i, correct? Now, I square is negative 1. So we get this as 4 plus 12i minus 9 times 2 plus 3i. So clearly, let's simplify this first. So we get 12i minus 5 times 2 plus 3i. And now we can apply the distributive property. Multiplying by 12i first, we get 24i, and that gives me 12 times 3 is 36, I square. Then with negative 1, we get negative 10, and negative 5 times 3, negative 15i. Combining the like terms, well, this is negative. Let's go one more step. So 24i minus 36 minus 10 minus 15i. So what we get here is 36 minus 10 is minus 46, and 24 take away minus 15 means 9, right? So we get plus 9i. So that becomes the result of cube of 2 plus 3i, right? You can also say that the cube root of this is that. Perfect. So we could also say, so you can try this out, do the reverse. So check. That is cube root of minus 46 plus 9i is 2 plus 3i. Correct? So you could correlate in this fashion. Now let's take up the next example, which is question number 11. You need to evaluate I to the power of 99. I'd like you to pause the video, answer this question, and then look into my suggestions. We need to evaluate I to the power of 99. Now let's look into a few properties to solve this particular question, right? So let me just share with you that on a coordinate plane, we could represent real numbers on this side and imaginary numbers on the y-axis. So when I say I, so I is this, right? That is I, imaginary. And then this is I square. And this is I cube. And that is I to the power of 4, right? So as you multiply, it kind of circulates. It's like a circular function. So what I'm trying to say here is that I to the power of 0 is 1. I to the power of 1 is I square is minus 1. I cube is minus 1 times I, which is minus I. And I to the power of 4 is 1. Then if I do I to the power of 5, I multiply this with I, right? So I to the power of 6 is I square, which is minus 1. I to the power of 7 is minus I, and I to the power of 8 is again 1. So what you really find here is that there is a pattern, right? So the pattern to be noted here is that the number repeats. Do you see that? So if it is a multiple of 4, then we get 1, right? So what you realize here is that I to the power of 4n is equal to 1. You see the point? Correct? So if it is a multiple of 4, you get 1 as your result. That is very important to understand. Now we can always use this particular property to find our function. Perfect? Now these are the remainders when you divide by 4. Those are the remainders, correct? So I to the power of 4n plus 1 is basically I. So I to the power of 4n plus 2 is minus 1, and I to the power of 4n plus 3 is minus I. Do you see a pattern here? Now you can use this pattern to find any powers of I, right? So use pattern rule. To evaluate exponents of I. Is that clear? So in our question, we need to find what is I to the power of 99, correct? Now I to the power of 99 can be written as I to the power of 96 plus 3, right? Why do I write 96? 96 is a product of 4, right? Let me show you on the side. So if I have 99, and if I divide 99 by 4, what do I get? 4 times 2 is 8, right? Then we get 19. And 4 times 4 is 16. The remainder is 3. So basically, we could write I to the power of 99 as I to the power of 24 times 4, right? So 4 times 24 plus 3. Now the first part here is just 1, which is I to the power of 4 times 24, which is 1, times I to the power of 3, right? That is the meaning. So what we get here is I cube, and the value of I cube is minus I. So our answer is minus 1. Is that clear to you, right? So we can write down that the value of I to the power of 99 is equal to minus 1. Is that clear? So we use the function mod 4 also to evaluate these results. Perfect. I hope this concept is absolutely clear. And also we'll be using this particular concept that the value of I, when multiplied by itself, moves counterclockwise on a plane to give you the value. I hope that makes sense. Now let's look into the next question, which is question number 12. Question here is, if z equals to 2 minus 3i and w equals to 1 plus 2i, find z times the conjugate of w minus w times conjugate of z. So let's write down what we are given. So we are given z as equals to 2 minus 3i. The conjugate of z is 2 plus 3i. We are given w as 1 plus 2i, and the conjugate of w is 1 minus 2i. We need to find the product. Z w conjugate minus w z conjugate, correct? So we have 2 minus 3i times the conjugate is 1 minus 2i minus w is given to us as 1 plus 2i times the conjugate of z, which is 2 plus 3i. Is that clear, right? So that is what. So let's expand and simplify. So we get 2 times 1 as 2. 2 times this is minus 4i. With negative 3i, we get negative 3i. And that when you multiply, I square makes it negative, so you get negative 6. Now here, let's put them in brackets. With 1, when you multiply, you get the same numbers, 2 plus 3i. And with 2i, you get 4i. And then that becomes negative sign, 2 times 3 is 6. So let's combine the terms. 2 minus 6 is minus 4, and that is minus 7i, minus, within brackets we have 2 minus 6 as minus 4, and that is plus 7i. So basically what we have here is minus 4 minus 7i, change the sign, plus 4 minus 7i. And minus 4 plus 4 is 0, and we get minus 14i as our result. Is that clear to you? So that is the result of the given expression. Now here is the last question for us. This is kind of a bonus question for you. You can pause the video, answer this question, and then look into my suggestions. We have a very interesting question here, which is 8 plus 6i is equals to a plus bi whole square. Find a and b. I'd like you to pause the video, answer the question, and then look into my suggestions. Now, whenever we have two equal complex numbers, then we need to equate the real and the imaginary part. Okay, so let me rewrite this as 8 plus 6i equals to a plus bi whole square. So what we get here is the right hand side, a plus bi whole square, will be a square plus 2 times a times bi plus bi whole square, right? That's what we get. And this will give you a square plus 2abi, and this is minus b square. So we get the real part as a square minus b square, and the complex part as 2abi. Is that clear to you? Now, when they are equal, we have to equate the real and the imaginary parts, right? So the real parts and the imaginary parts, correct? They should be equal. So we get two equations. 8 is equal to a square minus b square, and 6i is equal to 2abi. Correct? So we get two different equations to solve. Now from here, from the second equation, we can write a in terms of b, right? So we could write this as we can write b as equal to 6 over 2 or 3 over a, right? So when you divide, I and I cancel, 2 goes 3 times and a comes in the denominator. So b equals to 3 over a. Substituting b equals to 3 over a in our first equation, we should be in a position to solve, right? Let's say this is equation 1 and that is equation 3 for us. We'll term this as equation 2. Now let's try to solve. So what we have here is 8 equals to a square minus b square, and b is 3 over a. So we have 8 equals to a square minus 3 over a whole square. So 8 equals to a square minus 9 over a square. Multiplying with a square, we get 8a square equals to a to the power of 4 minus 9. So we do get a quadratic equation. To solve this, let's bring all the terms together. So we get a to the power of 4 minus 8a square minus 9 equals to 0. Now we can do product and sum. So 9 times 1 is 8. So we could get this as a square minus 9 times a square plus 1, right? So that should be fine. So that gives us two solutions. One of the solutions from here is that a square equals to 9, and here we have a square equals to minus 1, so which is not possible. A and b are real, right? So note that both a and b are real. A and b belongs to real numbers. Okay, so we cannot have this complex number. So we get a as equals to plus minus square root of 9, which is plus minus 3. So we have the value of a as plus minus 3, and the value of b is 3 over a, right? So from here we get the value of b as plus minus 3 over 3, which is plus minus 1, correct? So we get the value for b as well as for a, depending on if it is plus b, we got plus 1, right? So both positive or both negative. So keeping that in view, we can now write down that 8, so those are the two solutions, correct? So with those solutions we can write 8 plus 6i could be equal to So a could be equal to 3 and b is 1, right? So it is equals to 3 plus 1 I, let's write I here, whole square, right? And this is also equal to minus 3 minus 1, right? So this is, or we have minus 3 minus I whole square, either way. So we can write 8 plus 6i as 3 plus I whole square, basically, right? That is one and the same thing. So that is how we can find the value of a and b. So we get our answer that a equals to 3, then b equals to 1, and if a equals to minus 3, then b equals to minus 1. Is that clear to you? So I hope that makes sense. With that, we come to an end of our introduction to complex numbers. I hope you have understood and enjoyed this process. You will also note that in the last example, we actually found square root of 8 plus 6i. If you rearrange this, right, so you could see this as also square root of 8 plus 6i was equal to plus minus 3 plus I. Does make sense to you? So we did find square root also, and this is a good method to find square root of a complex number. So I hope that makes sense. So with that, we come to an end of our introduction to complex numbers. I hope it really helps to understand the topic. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.